Good afternoon, ladies and gentlemen. And my name is Mark Betcher, and on behalf of Nesma, New South Wales, I'd like to welcome you and thank you for your time today to attend our day at the test station. We're going to be conducting 3 tests today. They'll all be followed by a walkthrough to witness the result, and then Max Carstead from Cove Test Station is going to give a brief talk on the results of the tests. In addition, there's some heat rise tests which have been going on all day and all morning. So there's some results. Max has had them running for some time now, so there's already results happening as we speak. We're going to have them as enclosed and unenclosed, 4 different types of heat rises. I'm just going to quickly run through, tell you what the first test is all about. The first test will be a bolted short circuit on main bus bars in the far right-hand section of the switchboard, which is down there. So it's just the straight bars. The setup is the bus bars are spaced at 100mm centres. We've used Fibon bus bar supports, which are commonly used in the industry. Supports have a maximum spacing of 500mm, and a test current of 50 kA will be applied to the switchboard for 1 second. The objective under normal circumstances would be that the bus bars will withstand the test current. The switchboard will comply with the requirement of ASNZS 3439 clause 82325. And the bus bars shall not, paraphrasing the standard, the bus bars shall not show any undue deformation. The supporting insulating parts shall not show any significant signs of deterioration, and it must be capable of withstanding a dielectric test after the short circuit. That's what should happen under normal circumstances. Our objective is to demonstrate what will happen or what can happen when the bus bars aren't supported correctly. Whilst the supports themselves are appropriate, they've been placed too far apart.
What we have is the busbar system that you saw have a little bit of trouble. As probably indicated to you, the test involved a prospective current level. So at the top of the board there was a prospective 50,000 amps at 440 volts. When we've turned the current on, we've had a current duration for just on 10.5 cycles, so just over 200 milliseconds. In that period, the average current dropped to 48 kA, so that meant the prospective of 50 kA has been reduced by 2 kA because of the impedance of the busbar system. In that test, that bar on the far left-hand side received an initial asymmetrical peak of 100.7 kA. So when we look at the slow motion, you'll actually see that that initial bar has been repelled from the other 2 phases, and so that's broken the support on the left-hand side. Now what you'd expect is that particular type of busbar support system would normally be used at about 150-200 centres maximum, but by increasing it to a phase spacing of 500mm, we don't have the adequate support on the bar. You can see the bars vibrating there. And they're vibrating because you've got the sinusoidal RMS current still going through the bar work, and so you're getting this attraction repulsion at 100 times a second due to the 50 Hertz AC supply.
I'll just run briefly through what the second test is going to entail. We're going to have a bolted short circuit on the load side of a 200 amp circuit breaker. The Test 1 section has been disconnected away from the rest of the board and it's been isolated. The setup is going to be a 200 amp circuit breaker mounted in its own compartment. Circuit breaker is fed from the main bus bars. A bolted short circuit at the end of a short length of cable as required by the standard, and a test current of 50 kA will be applied to the switchboard. The objective under normal circumstances would be that the circuit breaker will withstand the test current and can be operated manually. In addition to the results to be obtained above, the circuit breaker must also be able to be reclosed after the test to be able to check the dielectric properties. Our objective is that we have deliberately undersized the fault capacity of the circuit breaker. This will demonstrate, hopefully, what can happen when a circuit breaker or when circuit breakers that are used that do not have the appropriate KA rating.
Well, everybody, what we've seen is a circuit breaker this time, subjected to the same fault that was on the busbar system, which that fault particularly trashed the busbar system. In this instance, what we're seeing is the circuit breaker with a set of cables on the load side connection down to a bolted short circuit. When we actually play the test, what we see is a couple of things occur. You will see a little bit of arcing right at the top of the circuit breaker, and then you also saw a lot of arcing at the bottom red phase terminal of the cable. So the fault had actually got onto the cable system through the protective device. The actual bottom cable lug broke. So the crimped ferrule part was still on the cable, and the flag that's bolted was still bolted to the short circuit. So the immense force has actually ripped the cable lug in half. The cables were allowed to move because they only had PVC cable ties that were clipped and wrapped once. What we find is, for a cable tie installation, normally with the PVC ties, you need to use a multiple wrap on the cable tie, and what that prevents is the actual force of the cables moving apart to put force on the very weak tooth catch arrangement that's at the locking part of the cable tie. After that, that's where you're getting that arcing, is that the cable tie is starting to rip. You're seeing the bit of arcing at the very top red phase circuit breaker terminal on the line side. And then the red phase breaks away. We've still got the three-phase arc at the top. The excessive amount of arcing is due to the very high fault current being supplied to the moulded case circuit breaker. And then when everything clears, you'll see that the cables have all broken away, all the cable ties. And in this instance, the circuit breaker is still there. I believe there is some reset capability of that particular breaker. That's probably because it's an older make, reliable one, which has a lot more material in it compared to some of the newer ones, perhaps, especially when they're overrated. As far as assessment of the test result would be concerned, the cables pulling away and moving like that would be a deemed failure to the standard because they're no longer held appropriately and where they need to be. And the pass or fail of the actual circuit breaker would be deemed by it still being capable to be reset and passing its dielectric capability, but we haven't performed that test on that particular department.
Now we're going to wake you up. Third and final test for the day. Our third test is an arc fault started on the line side of a 200 amp circuit breaker. The 200 amp circuit breaker has only been installed to demonstrate a typical installation. It will play no part in the test as the fault will start on the line side. Fuse wire has been wrapped around the phases, and our objective is to demonstrate what can happen when a person is working on a switchboard that has not been isolated prior to work being commenced. The deadly explosion of fire and deadly gases that have claimed many lives.
quite a horrific explosion. That's why all of my staff turn their light switches on at home with broom handles. We don't go anywhere near it. Anyway, the net result is we had a bit of fuse wire, probably about 1.5 square mil, just bridging the terminals on the line side of the moulded case breaker. That's not too dissimilar to a bit of fuse wire that's left on for doing an IR test or a HV test, or a screwdriver left across the top of the breaker when the board's re-energised. So they are things that do occur. We did put a little bit of Lexan over the front of the unit. That was probably led to the noise being a little bit louder than normal as well, because there's no sort of pressure relief for that cell. So the only pressure relief that came was from blowing those 4 fixings off and then blowing the front cover away. So that's the to the extra loud boom. The arcing did continue. So from our measurement system, we found out that we had, once again, the same prospective current of 50 kA, but the arcing current was reduced due to the resistance of the arc down to, it started with about a 34 kA RMS, and it reduced to about 31 at the end of the test. The test itself maintained itself for 10 cycles, so 200 milliseconds was the on time for that particular test. And so in that 10 cycles of current, you saw the immense amount of damage that occurred to the assembly as a whole. As you can see, the huge amount of arc product, hot flame and gases that were generated, and our test cell is designed with 3 very large extraction fans to remove that. So if you're in a normal switch room where you don't have that extraction capability, there's no way you'd be able to see where your exits are or anything in that room.